Good morning, all of you TyBscPhysics student. We have to see here our subject is solid state physics. We have to interesting start the fourth chapter, which is the magnetism, and we have to know that idea of the subject of the electrostatic, that is considered as three part, which is electrostatic consider of the electric field, magnetostatics, and EM theory, that is electromagnetostatics. So in electrostatics consider as velocity which is constant or v is equal to 0, which is depends upon point charge, line charge, surface charge density, and electrostatic force which is considered as 1 upon 4 pi epsilon naught E square divided by R square, and that is considered as v is not equal to 0, and in magnetostatics that velocity constant, and magnetostatic that v is not constant, that depends variation of electric as well as magnetic field. So in this chapter we have to study here the concept of the magnetism, and introductory part which is considered as here the discovery, starting from the discovery of electron. This discovery of electron, which is known as high electrical and thermal properties of metal, which is attributed to the motion of the electrons in the inside the metal, and also the magnetic properties of the material, which are attributed to electrons in the orbit of the atom of the material. So these are consist of two properties of the material. So that electrical and thermal property, which is metals which is inside the material of the motion of the electrons, and in magnetic property that material which is attributed to electrons with the orbit of the atoms of the material. And this all magnetic effect in material can be explained on the basis of the current loop due to the orbital and spin motion of the electron. That orbital motion of electron, which is considered as the orbital angular momentum, and spin motion of electron, which is considered as spin angular momentum, which is see further in the next lecture. And this, due to this orbital and spin angular momentum of the electron, there is the magnetic atomic magnetic moment which is associated with it, and this intrinsic magnetic moment of the electron is the main source of the magnetism in the matter. So we have to consider in the magnetism that matter which is the base in the part of the experimental fact, that the presence of the bulk matter which is generally modifies the magnetic field produced by this current loop, and material have intrinsic magnetic moment, or they may have the induced magnetic moment due to the external applied magnetic field of the induction. So in this magnetism, so magnetic flux, that concept which arise, and monopole exponential or exponential of the magnetism, which is considered as monopole, dipole, quadrupole, octopole moment of the material in magnetism or in electric field. So that in electrostatics that electric monopole which are obtained, but in magnetism that magnetic monopole which is does not consist, because if you consider take a one bar magnet, and if we cut in the small pieces, and we have to observe that magnetic dipole which is observed, magnetic quadrupole which is observed, octopole which is observed, but magnetic monopole which is not observed. This is the main theory which is see on the basis of the behavior of the material which is placed in the external magnetic field, and that magnetic material can be classified as diamagnetic, paramagnetic and ferromagnetic materials. So which are classified that magnetic materials in three main types, consist of diamagnetic material, paramagnetic material and ferromagnetic material, which is analysis which is the depends upon the properties of the material. If we see the small idea of this corresponding material, so that diamagnetic material are those whose atoms do not have permanent magnetic dipole moment. So this is very important point once upon revise. So that diamagnetic material that whose atoms do not have permanent magnetic dipole moment. Paramagnetic and ferromagnetic material are those which have atom which have the permanent magnetic dipole moment. So these are the very important point. So diamagnetic material which has not permanent dipole magnetic moment, while paramagnetic and ferromagnetic material those which have atoms of having the permanent magnetic dipole moment. If we consider the diamagnetic material which weakly repel in the external magnetic field, so whatever material diamagnetic material which is placed in the external magnetic field, so that material which is weakly repel in the external magnetic field, and paramagnetic material which are weakly attracted in the external magnetic field, and ferromagnetic material which are strongly attracted in the external magnetic field. So that depends on the theory of the domain theory, and have the analysis or understanding the domain theory we have to get clear idea why we have to say that diamagnetic material which is weakly repel, paramagnetic material which is weakly attracted and ferromagnetic material which is strongly attracted in the external magnetic field. So in this chapter we have to see the understanding or discuss the microscopic properties of the material. So we have to interesting see here the main point which is the magnetization and magnetic field strength, and we have to know that what is mean by the magnetization. So that magnetization which is the magnitude of the magnetization vector which is defined as net magnetic dipole moment per unit volume, net magnetic dipole moment per unit volume, which is considered as or called as the magnetization. This magnetization induction considered as the capital B bar, that is considered as the magnetic field, and which is the sum of external field and the field produced due to the current loops of the electrons in the magnetic substance, which is related to the magnetization by the relation. So here Q's relation this magnetic induction which is denoted by capital B bar, and this is the sum of the magnetization and current loops of the electrons in the magnetic substance, that is mu naught m bar plus mu naught h bar, and this mu naught which is considered as the permeability of free space. And you have to see that in electrostatic that formula which is considered as E is equal to 1 upon 4 pi epsilon naught or epsilon E square divided by R square. So that epsilon naught which is considered as the permittivity of the free space, and here mu naught is the permeability of the free space, and here H bar which is called as the magnetic field strength, and this unit which is considered as magnetic induction which is Weber per meter square, and H that is the magnetic field strength, and M that is the magnetization which is the unit considered as ampere per meter. So if we consider the paramagnetic and diamagnetic substance, the magnetic or magnetization vector, that is m bar, which is directly proportional to or which is proportional to h bar. So that see in the equation 4.2, so that relation gives that magnetization vector which is directly proportional to magnetic field strength, that is h bar. So m bar is equal to chi into h bar. This chi, which is considered as the magnetic susceptibility, and chi is and magnetic susceptibility which is considered as the dimensionless quantity. And if the material is paramagnetic, that magnetic susceptibility is positive and the magnetization vector which is in the direction of the h bar. So this is important point. So for paramagnetic substance, your magnetic susceptibility is positive and magnetic vector, that magnetization which is the direction of the magnetic field strength. And if material is diamagnetic, then your magnetic susceptibility is negative and magnetization, the direction of the magnetization which is opposite to the magnetic field strength. So that we have to use the relationship which is for the ferromagnetic substance, and it should be noted that the linear relationship does not apply for the ferromagnetic material. So that equation gives the magnetic field induction which is equal to mu naught into 1 plus chi into h bar and mu naught into 1 plus x, which is considered as the mu m, and this mu m is called the magnetic permeability, which is mu m which is considered as magnetic permeability, and that mu m is equal to mu naught into 1 plus chi. So this substance may also classified in terms of the magnetic permeability mu m. So what is the relation between magnetic permeability and permeability of the substance which is given for the in paramagnetic substance? Mu m, that is magnetic permeability which is greater than the permeability of the free space. Diamagnetic substance, that magnetic permeability which is less than the permeability of the free space, and in ferromagnetic material which is magnetic permeability which is much greater than the magnetic permeability of the free space. So this is the classification of the magnetic material for considered as the paramagnetic material, diamagnetic material and ferromagnetic substances. So that give the relationship between the magnetic permeability and permeability of the free space. So in above the three substances, we have to see first what is the property of the diamagnetic material, so which is considered as the diamagnetism. And already we have to know that diamagnetic substance which are weakly repel when your material or the substance which is placed in the external magnetic field and have negative magnetic susceptibility. So diamagnetism is the small and has a very weak effect in the many materials caused by the reaction of the orbiting electrons to an applied magnetic field in the accordance with the Lenz's law. So that means by, so if material which is placed in the external magnetic field, so what is the interaction between external magnetic field and orbiting electron, so that depends upon and which is help to understanding by the Lenz's law. And in the diamagnetic material, the magnetization which is opposite to the direction of the field of the induction, which is opposite to the direction of the field material. And if we consider here, so your susceptibility which is negative, so the value of the magnetic induction B which is smaller in the diamagnetic material. So consider here the magnetic induction B, that is called as the magnetic field which is small of the material, and that material would not be or would be if the material is absent, that antimony. Example which is considered as this dimagnetism, which is considered as antimony, bismuth, mercury, gold, copper are the examples of the dimagnetic substances. So if we consider the magnetic material which is placed in the external magnetic field, it can increase or decrease of the flux density. So here main concept which is considered as what is meant by flux. So flux which is considered as the number of the magnetic lines, number of the magnetic field lines passing through cross section area, which is considered as the flux. And this diamagnetic material which is the reduce the density of lines of the forces, and while in the paramagnetic substances that increase the flux density. So that main point, if we place the magnetic material which is kept in the magnetic field, it can increase or the decrease the flux density. And if we consider that diamagnetic material, so that reduce the density of lines of the forces. And in the paramagnetic material, if we consider that increase the flux density. And this diamagnetic material or diamagnetism which is created by the circulation of the electron in atoms or the molecule. And such diamagnetism material which is considered as the susceptibility which is less than 0, and it is the independent of the temperature. So this is the very major idea of this diamagnetism. So once again repeat, so that diamagnetism which is considered as the which is weakly repel with its substance which is placed in the external magnetic field. Here the susceptibility which is negative and field direction which is opposite to the magnetic field or magnetic field induction. So and it is substance which is independent of the temperature, and that diamagnetic material have zero magnetic moment in the absence of the external magnetic field. So that is very main point. So consider the diamagnetic material have zero magnetic moment in the absence of the external field, and with presence of the external field, that material which have show the deflection of the molecule. When external field applied, so that formula which is considered as magnetic dipole moment opposing the field induced in the atom or a molecule. Okay, so that have considered, we have to know that that magnetization which is opposite to the direction of the magnetic field strength, that is H bar. So that in the paramagnetic substance may have diamagnetic effect, but it is much weaker as compared to paramagnetic. And diamagnetic substance which reduce the density of lines of force, which is while the paramagnetic substance increase the flux density, and which is described by here the diagram, the flux density in the magnetic sample and flux density in the paramagnetic sample with the susceptibility of water which is considered as minus 9 into 10 to the power minus 6, while that graphite which is considered as the minus 6 into 10 to the power minus 5. And if we consider in the figure, so that magnetic field strength direction which is passing through that substance or area, so what happens in the field line appearance here, which is show very clearful get idea. So what is the effect of the external magnetic field apply on the diamagnetic and paramagnetic substance? So what happens there, which is shown in this figure. So and depends on this diamagnetism theory, we have to see the point of the classical theory of the diamagnetism, or this theory which is considered as the Langevin theory of the diamagnetism. And this diamagnetism which is associated with the tendency of the electrical charge which is partially to shield the interior body from an applied magnetic field in an electromagnetism. So we are familiar with this Lenz law, and this depends upon the flux through the electrical circuit is changed and induced diamagnetic current which is set up the direction of opposed to the flux change. So that magnetic current which is considered as I, and if we see the relation between this I, Lenz law, so that depends upon here. So whatever change with depends to the time, which is the period of the revolution of the electron in the atom. So that if we consider very simple case, that electron which is revolving around the nucleus in a circular orbit, because we have to consider that in diamagnetism your electron which is appearance in the moving in the circular orbit or circular electron moving. So that consider as if we this circular moving electron, so that have shape considered as the radius r, and this electron velocity v, and electron revolving which is in the circular orbit consider the current which is given by I is equal to E by T, and this T is the period of the revolution of the electron. Here V is the velocity of the electron of the circular orbit, and the period of revolution which have two formula which is calculated by capital T is equal to 2 pi r divided by V, because of why, if this electron which is considered in the circular orbit, that circumference of this orbit which is considered as 2 pi r, and this T which is inversely proportional to V, that is the velocity of the electron. So that relation obtained here, T is equal to 2 pi r divided by V, and this equation which is substitute in I is equal to E upon T. So denominator if substitute the value of T, that is 2 pi r upon V, so that relation which have obtained here, I is equal to EV upon 2 pi r, EV upon 2 pi r. And if we calculate the magnitude of the magnetic moment due to the current, so that magnetic moment is equal to current into area of the loop, and already we have to calculated in here, so that current which is considered as EV upon 2 pi r. So that putting this value in this, so here M is equal to current, so that current which is considered I, and area of the loop, that area loop which is considered as circular, so that circular loop area which is considered as pi r square. So that's why consider here M is equal to I into pi r square, and this magnetic moment which is putting this value, both current and area of the loop is here. So magnetic moment which is considered here, so that r pi r square and denominator of 2 pi r, 1 r get cancel, pi get also cancel, so remaining M is equal to EVR upon 2. At this equation, that multiplying and dividing RHS above the equation by the mass of the electron. So multiply by numerator and denominator by mass of electron, that small m, and mass of electron which is considered as 9.1 into 10 to the power minus 31. So this multiplying this mass, so that relation will obtain here E upon twice m into mvr, and already we have to know that I have suggested that. So in the electrostatic system, so we have to consider here the orbital angular momentum which is considered as L is equal to mvr, that is related to the corresponding orbit of the atom or electronic orbit of the atom. So that capital M is equal to, which have given the relation E upon twice m as it is, and mvr that replace this the orbital angular momentum, that is small l bar. And due to this negative charge of the electron, the direction of the magnetic moment which is opposite to the that of the orbital angular momentum. So because we have to know that the that electron of the charge which is considered as the negative, that negative sign which is become here, so that's why we have to consider here or say that the direction of magnetic moment which is opposite to the orbital angular momentum. And if we see in the figure that direction of the magnetic moment, which is considered as according to the Lenz's law. So that diamagnetism or origin of the diamagnetism of the Lenz's law, the atom with its circulating electron acts like as a inductance in which the counter of the electromotive force which is produced in the accordance with the Lenz's law, and this since called as the no resistance which is encountered by the electron during its motion and around the nucleus, which is increased velocity and does not diminish with time. So let us consider the effect of the external applied magnetic field, that is considered as the B, which is the magnitude of the external flux which is considered as phi, and through the closed loop if we consider here, so that external magnetic field which is applied as this closed loop, and default direction which is see here the anti-clockwise direction, so that your magnetic flux which is considered as phi is equal to consider as the area of loop which is pi r square, and magnetic field induction which is B, so that flux which is given as phi is equal to pi r square B. And see in the field varies with time, magnitude which is induced EMF which is considered as epsilon is equal to minus d phi by dt. Okay, because we have to change that flux which is changing with the time, or change with the time, and we have to know that already that phi value which is considered as phi is equal to pi r square B, and here pi r square which is constant factor, and your variation of the magnetic field. So take the derivative of dB by dt, so that if the induced electromotive force which is act around the loop which is considered as epsilon is equal to twice pi r, that is which is considered and the electrostatic field, so that is epsilon is equal to twice pi r into E, and this twice pi r which is considered as the circumference of this loop. And if we equate this both equation, so that epsilon is equal to twice pi r E and epsilon is equal to minus pi r square dB by dt, so that relation of the electric field which is considered as minus r by 2 dB by dt, and this electric field which is exert on the force E, which is due to the electron accelerated, and this electron accelerated field which is considered as m dV by dt. And if rearranging this equation, so by dV by dt is equal to E into E divided by this m, and if we doing the calculation of this further, so dV by dt is equal to if we placing the E value, that is electric field strength which is r by 2 into dB by dt in this equation, so that equation which is given here minus ER by twice m into dB by dt, and thus the time of the magnetic field induction which is changes by the variation in the magnetic field induction, and velocity which is variation of the with respect to this, so that change in velocity which is considered as minus ER divided by twice m, so that is dV by dt which is considered as variation d, so that is delta V, and dB by dt which is considered as the delta B, so delta V is equal to minus ER by twice m into delta B. And using for this equation which is considered as this m is equal to EVR by 2, and if we the variation of this equation which is considered as delta m, so that equation which is EVR by 2, so that change in this magnetization which is considered as the change in the, or which is proportional to the change in the velocity of electron, and which is given by ER into delta V. And if we place the value of delta V which is E minus ER by twice m into delta B in this equation, so that magnetization change in magnetization value which is obtained here minus E square R square divided by 4 m square into delta B. And this know that this equation which is obtained here B bar, that is magnetic field induction, is equal to mu naught H. We have to see already this idea. Here B is the magnetic field induction, mu naught is the permeability of the free space, and H bar is the magnetic field strength. If we putting this value in this above equation, so we get the magnetization relation, which is minus mu naught E square R square divided by 4m square into change in this magnetic field strength, that is delta H. And if we want to calculate the magnetic susceptibility of given equation, so that we have to know that magnetization vector which is given as chi into H. So if we want to this chi calculate, so that which is given by above equation, so that value which is obtained for minus mu naught E square R square divided by 4m square. And here there are the n atoms per unit volume, so that is number of atoms per unit value. So place the value of the m, and the volume of the susceptibility can be here. So mu naught n mu naught E square divided by 4m square, this is the constant value, and summation of R square. So that if we consider the many loops here, so that summation of these loops radius square, and this summation of the above equation which is extends for all z electrons of the atom, all z electrons of the atom, and which is z is considered as the here atomic number. So this value which is gives the summation of R square is equal to z into expectation value of the R square. And if we calculate this expectation of R square, that is means, which is considered as mean square of perpendicular distance to the field axis of passing through the nucleus, so that is considered as expectation of R square is equal, that is the mean square value, so is equal to mean square value of x square plus mean square value of y square, that is expectation value of R square is equal to expectation value of x square plus expectation value of y square, that is considered as the perpendicular distance of axis passing through the nucleus. And this mean square distance formula which is obtained from, which is considered in if the 3-dimension space, so that is capital R square, expectation value of capital R square is equal to expectation value of x square plus expectation value of y square plus expectation value of z square. So for this spherical symmetric change charge distribution of the charge, we have expectation of x square is equal to expectation of y square is equal to expectation of z square, which are equal. So that we have to say that expectation value of R square, which is given as 2 by 3 expectation of R square. This is the mathematical part, which is further see complete the this chapter. So we have to see on the blackboard also. And this the susceptibility value which is given by using of this equation. So we have to get value mu minus mu naught n z square divided by 6m into expectation of R square. And for this following conclusion, so which is can be drawn from this Langevin formula, because we have to see here the classical diamagnetism theory. Okay, so this classical theory of diamagnetism, and which is considered as the Langevin theory, so gives the idea about the following conclusion for this Langevin formula gives here. So first one, the all substances exhibit the dimension through it is masked by other magnetic effect. Second conclusion, which is considered as the susceptibility of diamagnetic material, which is proportional to the atomic number. So that's why we have to here give the formula x is equal to minus mu naught n z e square divided by 6m into expectation value of R square. So that relation between this chi and this z, so which is directly proportional to z. If we consider atom is bigger, so that susceptibility value also more. And for diamagnetic material, susceptibility which is independent of the temperature, because does not concept which is arise here the temperature. And if a perfect diamagnet such as a superconductor includes all the flux from the interior of the material, so that B bar which is considered as 0 and chi is equal to minus 1, so that is negative value of the susceptibility of such material. So due to this we have to see from the introduction part to the what is meant by the substance which is depends upon the depends upon the magnetism, considered as three types of the substance or three types of the material which is here. First of all, the diamagnetic material which is placed in the external magnetic field which is weakly repel, paramagnetic material which is weakly attracted, and ferromagnetic material which is strongly attracted. And after that, see here the classical theory of the diamagnetism which is considered as Lagrange theory. And up to the this lecture is complete. Next lecture we have to consider here the point which is considered as what is meant by the superconductivity and paramagnetism material and ferromagnetism material, which is considered in the next lecture. So thanking all of you.